Hi friends, in this video we're going to derive the Bernoulli's equation. So consider a pipe with varying diameter and height through which an incompressible fluid flows. Let's also assume ideal conditions for the flow, that the fluid density is constant at both points. Also, we're going to assume that the energy is conserved as there is no friction forces, the viscous forces. Okay, so if you look here, we have the area 1 at point 1, area 2 at the second point, and this is the reference point, and the height from point 1 to this reference point is y1, and for point 2, y2. And this is the direction of the flow. This is the velocity of the fluid at this point. This is the velocity of the fluid at the first point. The fluid is flowing, so there is a force. And since there is force and the fluid is moving, changing distance, so there is going to be work done. So the work done is going to be equal to force 1 times the small distance we take in part 1 minus force 2 times the small distance 2. So now, remember, force is the same as pressure times area. So 1 minus 2, sorry about that, minus P2 A2 dx2. Also, recall that volume is area times distance. So here we have area times the change in distance, which gives us a change in volume. So, as we have shown ideal conditions, the change in the volume is going to be constant. So the dv1 is going to be equals to dv2, which is just equals to dv. So we're going to have p1 minus p2, sorry about that, dv. So that's dw. Let's leave this equation for a moment and name it equation 1. Next, we're going to consider work done is the same as change in kinetic energy plus change in potential energy. Now, let us move to the difference in kinetic energy. Recall the formula to look for that kinetic energy is half mass times the velocity squared. Now, considering these 2 points we have in our diagram, the diameter at point 2 is relatively smaller compared to the diameter at point 1, so the velocity at point 2 will be relatively higher compared to the velocity at point 1. Therefore, our kinetic energy difference will be half m2 v2 squared minus half m1 v1 squared. Now, please don't get confused. This v doesn't mean volume. This v implies velocity. So don't get confused with this dv. This v and this v are not the same. The v in the kinetic energy equation means velocity. So keeping that in mind, now let's move on to the potential energy. So the change in potential energy, we can see from the diagram that the height at the height of point 2 is relatively higher compared to the height of point 1. So our mechanical energy is going to be m2g y2 minus m1g y1. And this is going to be density times g dv y2 minus y1. And this is going to be changed in potential energy. So leave this as third equation. Now we can see that equation 1 is equals to equation 2 plus equation 3. Now put these two equations together. We're going to have P1 minus P2 dv is going to be equals to half rho dv of v2 squared minus v1 squared plus rho g dv y2 minus y1. We can cancel out this portion of the equation. We're gonna be left with p2 equals to a half rho v2 squared minus v1 squared plus rho g y2 minus y1. If we rearrange this equation, we're gonna be left with p1 plus a half rho v1 squared plus rho y1 is equals to p2 plus half rho v2 squared plus rho g y2. This is Bernoulli's equation. So thank you for watching, and let's meet in another video.